Hello? Am I audible?
Let's start off. So this is likely to be the first of maybe a series of talks, what I'm calling the essence of learning. We're going to start really simple and with really simple concepts and get progressively kind of harder. And what I've done is I've actually set it up as a course. And it's available to you at courses.univ.ai, TEOL. Let me see if I can make this a bit bigger so you can see it, but I'll actually type it into the Zoom chat, which may be the smarter way to do this. So let me do that to everyone. Courses.univ.ai, TEOL, and TEOL stands for the essence of learning. And if you haven't created a Univ.ai account yet, you should probably create one. You can do it from this website. There's this little doodad which you can click. Let me show you that. On the right side over here, which will give you a choice to log in if you don't have an account, and you can create yourself an account. I mean, there's no need to do it for the lecture per se, but you should do one, after that. And the reason you should do it is the following. We have a discussion forum, and the discussion forum is at discourse.univ.ai. And on that discussion forum, I've created a category for the essence of learning. And we can talk about questions about this, as much as we like on this. This is always permanently going to be there, over there. So over here.
Rahul, sorry to interrupt.
Yeah.
Someone has a comment that they can't see your screen. Is the screen visible to everyone, or?
Is it, can people not see it, or is it too small?
It's a bit small for me. I got a comment on the chat saying that it's not visible to them. So
okay, then let me change the camera, and I can always change the you know what? I can always do it.
So he's not sharing his screen per se. You'll have to pin his video to be able to see.
Yeah, I'm not sharing my screen.
Yeah, he's not sharing his screen, so it's his video which you'll have to pin. So it's split with his video and the screen parallelly.
Okay, I've pinned his video.
Yeah, so you'll have to pin his video to see the screen.
Yeah, I think I've spotlighted his video. Let me know if everyone can see it now.
Yeah, we can.
Yeah, cool.
Yeah, Rahul, go ahead.
Go ahead. Okay.
Yeah.
One of these days, I'll figure out all the Zoom stuff. I haven't quite figured it out yet entirely. Okay, so let me put the URLs on here. Let's see. So it's courses.univ.ai to get an account, and it's discourse.univ.ai. Oh, I spelled that badly. And that's to do the discussions afterwards. And you needn't do either if you don't want to right now. The course itself is on courses.univ.ai TEOL, so you can follow along if you want to go there. Okay. So without ado, let's actually, without much ado, let's actually start up. I think I might try something over here. Let me just actually try and share my screen over here on top of this. Does that work differently? Can you see it better at this point?
Yeah, I see it better.
Better.
Yeah, okay. So that may be a kind of like a reasonable way to do stuff. Okay, but I'm actually unpinning this, so give me a second. So this is going to be a much longer course, but today is the kind of like a demo class from it. And we're going to learn about what goes into learning a model and how to find the right model. So this is basically talking about how fitting happens, and then how do you actually find the right model to fit something. And then later we'll go into much more detail, and you can look this up on the website. So our basic structure of today's talk is going to be learning a model and then finding the right model. And in learning the model itself, there's going to be 3 parts. There's going to be risk-n models, noiseless learning, and noisy learning. And some of these things may be a little bit broken right now, but we'll fix those. You just need to pay attention to the slides. Okay. So risk-n models is what we'll start off with. And let me find my screen over here. We'll start off on it. So stop share. Let's go back to a different scene. Okay. How do machines learn? And so this will be a very kind of interactive session. I will keep sort of like stopping myself and asking you questions. When I do that, please, just sound out the question. Just interrupt, unmute yourself, give me the answer, make a comment, whatever, and then go back on mute. So
Excuse me, sir.
Yeah, go ahead.
Sir, could you please go back to the share screen mode, because in this view it's kind of blur.
Is it more blurred in this view? Okay, thank you. Thank you for interrupting then. Let me do that. Okay, let's actually just go over to the share screen mode. There we go. And let's open the window. How about now?
Best.
Better?
Best.
Thank you. Okay. So our first thing is, we want to fit a model to data. Here is some data. So we would like to learn what function or model, these are the words we're going to use, generated this data, okay? So what does it mean to say generated this data, right? That's probably the first question you want to ask. It does not mean that the data came directly from the function. It means that somehow or the other there was some kind of physical process, some social process, some other process that gave rise to this data, but there was also some regular kind of noise in it. Why noise? Noise tends to happen sort of like all over the place, right? I mean, if you're measuring something with a ruler, you're going to have some noise because you didn't sort of like attach the ruler's ends kind of properly. If you're in a credit bureau and you're trying to figure out whether I'm going to default on my loan payment or not, you don't know all the stuff about my life, whether I just got laid off from a job or something of that sort. And so if there are 2 people, exactly the same salary, one just got laid off and one does not got laid off, then the prediction for one may be default and the prediction for the other may be no default. So all of these things generate noise in our system. Our function to predict this kind of person's credit score may be a perfectly reasoned one, but perfectly reasonable one. But beyond and above that, what happens kind of depends upon the situation. Okay, so we don't know what this function is. And in fact, think about it, you're not God, so nobody's telling you what this function is. And because nobody's telling you what this function is, hey guys, we should at some point shut off the waiting room, because I keep getting these waiting room messages coming across my screen all the time.
Rahul, I'll change you from the host. I'll take the host back. So
Okay.
you won't get those. Yeah.
Okay.
Yeah.
Thank you.
Go ahead.
So we do not know what this function f is, and the best we can do is to find some other function g that fits this data best. As I said, we're not God, so we don't know what generated the data. So we try things, and hopefully they work, right? Okay, so that's the basic setup of our situation. So to make this a little bit systematic, let's organize our functions, and we'll organize our functions into something called hypothesis space. So what's a hypothesis space? Is just a bunch of functions. It's a big fat name for something very simple. It's just a bunch of functions. For example, look at the function I've written on the left over there. It's basically going theta 0 plus theta 1x plus theta 2x squared plus theta 3x x cubed and so on and so forth up to some degree of the polynomial d. So this, as you probably know from math class way back in the past at some point, is a polynomial. An example is 4 plus 5x, or 4 plus 5x plus 6x squared, or 4 plus 5x plus 6x squared plus 7x cubed, or something like that. Anything, cook it up, right? So when I go to x cubed, that's an order 3 polynomial. When it's like squared, it's an order 2 polynomial, and so on and so forth. So these are the sort of like different polynomial complexities that kind of come up. Okay. So what we're going to do is we'll organize these hypothesis spaces by the degree of the polynomial. So let's say all the linear functions is one set. All the quadratic functions is another set. All the cubic functions is a third set. All the quartic functions is a fourth set. And we'll call each of these a hypothesis space. Okay, so that's going to be the game we'll play. Now, for example, the hypothesis space H1 is all H1 of x. Anything of the form theta 0 plus theta 1x is the hypothesis space H1. And H20, which is the other hypothesis space we're going to kind of concentrate on today, for reasons that will become clear very soon, is the set of all 20th order polynomials. Okay, and this is how you sort of like define these kind of polynomials in Python. Here's a little example, and here's a little plot. Now, I want you to see this plot and tell me if there's something interesting that you notice about the green plot, the green line, or the green curve rather. After all, it is a cubic.
The other two curves seem to touch the green plot.
They do, but what's weird about this green plot?
Very large number of positions.
Very large negative values, right? And so let's ask the question, why do you think there are very large negative values? Look at H3 on the left and tell me why you think there are large negative values.
It has got an x cubed term.
It's got an x cubed term, okay. So that's putting, and at negative values, that's putting a large amount of negative value, agreed, okay. So at minus 10, you are seeing minus 10 to the 3, which is minus 1,000, and multiplied by 5, that's minus 5,000. What else?
Your coefficient of x squared is also negative. So that also
Coefficient of x squared is negative and it's large, right?
Yeah.
Okay, so I think you got it. The point I'm trying to make over here is that if you have large sort of negative terms, things becoming largely negative or large negative coefficients in polynomials, you can get extremely large values both on the positive side and on the negative side. So just keep that in mind. That'll be kind of important as we go forward. Okay, so let's ask a question. What does it mean to fit? So that's that previous data which we saw. And we're asking the question, what does it mean to fit a function to this data? So if you saw this plot over here, how would you think of fitting this data?
Minimize the vertical errors.
Minimize the vertical errors, right? Yeah, absolutely. So you might say minimize the vertical errors, and how might you do that? We just add all the errors up?
at least square and minimize.
And why would you square them?
Because otherwise they might get cancelled, the positive and negative errors.
The positive and negative might get cancelled. Good point, right? So we could take the absolute values and add them too, right? If we wanted to fix that problem. Make sense? But as you said, and you came up with a good suggestion. Let's just square them. Let's just take the difference and square it and add it, and this way we won't have this problem. Okay, so there you go. So that's the way you would do this. Just change one thing while I'm at it. Change my camera to be.
So.
Okay, so that's, yeah, go ahead.
Yeah, so the previous, in this particular side, RD, whatever has been written, the sum of square errors, is it also the cost function?
This is also called a cost function. The risk function, cost function, it's the same thing. Error, okay. You'll see these words, absolutely, you'll see these words used used interchangeably. And notice that thank you for stopping me there, because one thing I forgot to say, which is notice the notation over here. It's saying R, the risk or the error on this data set D, as a function of some hypothesis H, right? So we have some hypothesis H, which belongs to the set of all possible straight lines, the capital H1, so to speak. And this is the error associated with it. And so now what's my idea going to be to fit?
Minimize it.
I'm going to minimize it. So kind of the word, I mean, visually, what does that mean? I'm going to sort of like put every possible straight line out there, right? Which I can find. Every possible member of the hypothesis set, capital H1. Every possible small h1 function, I'm going to put it there. And I'm going to find that function, that straight line, which minimizes the error. Make sense?
Yeah.
So in other words, this risk or error is actually a function of a function.
Yep.
Yeah. So you're finding the function which minimizes the error. Of course, you do it in a very simple way, right? You say it's slope plus, you say it's intercept plus slope times x, and you'll differentiate with respect to the slope, and you'll differentiate with respect to the intercept, set that to 0, and boom, you got your answer of the slope and intercept. And once you got your answer for the slope and intercept, you combine them together, and you get the best fit line. So does that idea make sense?
Yeah.
Yeah? Okay. So keep that idea in mind, okay? So that's the idea we're going to go through. Does this need to be a straight line, or can it be anything I want?
Anything.
It can be anything, right? It could be a neural network. It could be a polynomial. It could be just about everything I wanted.
Depending on the data.
Yeah, depending on the data, right? I might choose something else. Okay, so far so good. All right, so let's actually do something fun and funny. This is a sine curve. F of x is a sine curve. Actually, to be very precise, it's sine of pi times x. And I've taken the sine curve and I've added some noise to it. And then I've removed the curve and I've just left the data that came out of it. So this is about, I think I generated 100 points to make this graph for you. Okay. So if there is noise, I will still call f of x is equal to sine of pi times x, my generating function, my generating model. If there's noise, I'll add it in as this term epsilon over here. In the situation where there is no noise, I put epsilon is equal to 0. Then my y is just equal to f of x, and I'll get a curve that looks something like this. And you can see this basically just is exactly on the sine pi times x line. And this one isn't because I've added some noise in. Okay. So fitting a hypothesis to any of these functions is what we want to do. But specifically, I'm going to call fitting a function in the situation in which epsilon is equal to 0. I'm going to call that approximation because that's our usual sense of approximation. There's no statistics here. It's just that you said, hey, I've got some data. It's come from a function. Find me the function. And I'm like, well, I didn't know it came from a sine. I'm going to try all kinds of things to try and fit it. That's the game I'm going to play. So far, so good. Any questions?
Nope.
No? Okay.
I had one question.
Yeah, go ahead.
While we're calculating the error, all we know is the data points, and so we're subtracting our hypothesis from the data points.
That's right. So we are calculating our hypothesis at the x's of those data points.
Yeah.
As you
so
see,
if we wanted to find the approximation, then how would we know the so the y contains the function value plus some noise. So how would we subtract the noise? How would we know about the noise?
We don't know. We can't subtract the noise out.
Right. Okay.
Yeah, you're out of luck. You can't subtract the noise out. So you'll just be doing y minus h1 of x.
Right.
Squaring it, adding it over all the points you have in your data set, all these 100 points over here. That's what you'll be doing.
Thanks.
Okay.
I have a question as well.
Yes, go ahead.
In the previous slide, the equation, did that represent something similar to a line y equal to mx plus c?
This equation here?
No, the next slide.
Next slide.
Yeah, this one.
No, it's saying that I don't know what f of x is. This is talking about the generating function. See, imagine you are God, okay, for a second. And you said, I'm going to give Rahul some data, which has come from a sine curve, and I'm going to add some random noise into it. That sine curve is this f of x, okay? Then you came to me and you gave me the data, and you said, ha ha ha, I'm a sort of like, not so nice God. I'm actually going to give you this, but I'm not going to tell you which curve it came from. You figure it out yourself.
No, my question is, does it depict y equal to mx plus c? Like,
no, that would be a straight line, right?
Yeah. Okay. So here you're trying to say that the f of x, the function, can be any type of line.
Any type of anything. It's some kind of it's a function that was generated somehow. Right?
Okay,
It need not even be a very explicit process, right? It could be some kind of weird physics differential equation solving. It could be, a sine curve like I did over here. It could be data coming from a self-driving car. It could be anything.
Right. Okay. Thank you.
Yeah. So it's what we'll call the target or the generating function. We're trying to figure out what this function was.
Just a doubt, but in that sense, then the noise also may not be additive all the time, right?
Oh, absolutely. Noise may not be additive all the time. So I've taken only one situation here where the noise is additive. You're absolutely right. The noise may not be additive, and it may not even be it may not even have the same characteristics at every point. But if we can't solve the simple problem, we won't be able to make any headway on the more complicated ones, right?
Yeah, cool. Makes sense.
Yeah. So let's just talk about additive noise coming from some simple noise model of some kind or the other. But let's even actually go simpler. Let's start by saying no noise. We just want to fit this. The funny thing about this is that nobody told us that this was a sine curve. And we never went through school, so we never knew this was a sine curve. And so we want to figure out what it is. So what do? We come up with the functions we know, the polynomials, say for example, and try and fit this curve. So that's the game we're going to play. There is a complication though in this game. The complication is that, suppose I didn't give you all 100 of these points. Suppose I only gave you about 30 of them, or 20 of them, or something like that. And why would you think of something like this? Well, think of elections, right? So there are elections coming up in the US very soon. The US has about 300 million people. Is it humanly possible to go ask 300 million people what they are doing? Who they're going to vote for?
Not at all.
Not at all, right? What do you typically do? What does a pollster typically do, right? So they'll go out and ask 1,000 people. And they'll ask those 1,000 people who they vote for, and they'll try and actually get the 1,000 people from all walks of life, right? Men, women, white people, black people, Asians, all kinds of stuff. And they'll try and balance it across these things, at the same level as the population has those different mixtures of groups. And then they'll ask people, and people will tell them. So basically, you're trying to predict who's going to win the election from a sample. And that's what our life usually is like. We don't get all the data because we don't have infinite resources. We don't get all 100 points. We get 20, 30 points. And we are asked to tell what this function f of x is that generated this data. So is the setup of the problem clear?
Yes, Rahul.
Yeah? Yeah. Okay. Yeah. Okay, so we don't necessarily even have a population of like 100 points or millions of people. You have a sample of 1,000 people or a sample of 30 points or something. Okay, so let's go. Let's do this. So we're not all the details of the code and the Python and everything I'm not going to talk about today. This is meant to be a more sort of like, you don't need to know Python to follow what I'm talking about right now. But all the details of how these things were fit and everything are there in the notes and the notebooks, which are on the website. So please go take a look at those, and we can go from there. Feel free to ask me questions either on Discourse or on our Slack, and we can have conversations about it. So here is my best fit straight line to this. Okay, how did I do it? I essentially said, okay, this is my data. Let me say h1 of x is theta 0 plus theta 1x, and then let me subtract each one of those, square those, and figure out what theta 0 and theta 1 should be, right? Find the one that has the minimum distance. And this is what it looks like. Do you think this is a good fit?
No, sir.
No, right? It's a kind of bad fit. No. Okay. But it's a fit. It does roughly get this kind of idea that the sine curve looks like it's going up, right? Of course, if I do one more cycle of the sine curve, everything will go crazy. So, you know, it's a little bit of a lie over there. Okay, now, say I have a sample of only 20 points, right? The sample is these orange squares. And I now try and plot. I now try and do a fit. And this fit is now shown to you by this orange line. Now it gets the rough idea right that the sine curve is kind of increasing. But it does not get the same, it does not occur at the same place, right? As the blue line, which I fit on the entire population. So what would happen if I took a different sample? Would I get the same orange line?
No.
No, we won't.
No, right? Because it depends on how I chose those 20 points from the sample, right?
Yeah.
So what's the advantage of having large samples?
Lesser error or lesser noise, like your answer will be more precise.
The answer will be more precise and closer to the answer you got on the population, right?
Yeah.
So that's kind of intuitive. That makes sort of intuitive sense that that's going to happen. So you will have less error. Exactly. That's. Let me see. Do I have the slide here? No, I have that slide in the next one. Okay. So, yeah. So absolutely. You know. So that's the kind of effect you're going to get. You see, this approximation is bad, and the sample approximation is just as bad. They both get the rough direction right. You know. And you get, and that's I guess the best we could expect of this model. Okay, so let's just recap. What have we done so far, right? So far, we've done y is equal to f of x over here. That's some target we have, and from this target we have some data. Maybe we add noise to it. Maybe we don't add noise to it. We'll come back to this this noise situation later. Okay. Then you have some input distribution P of x, which is basically saying how are the x distributed across. You can see that, for example, in the sine curve, the blue x's are distributed very uniformly across the entire -1 to 1 range over here, whereas the orange ones are distributed somewhat differently, as you might expect, because it's a sample. Once you get that, you put those things together and you have the x and the y's, and you have a learning algorithm out here, which is linear regression over here, or polynomial regression over here, where you're basically taking this risk, which is the f of x minus what you predict, squaring it, and then minimizing it with respect to the to the parameters of the line, or the parameters of the quadratic function, or the parameters of the cubic function. So that's the basic idea, okay, of this system. Okay, so here's an example. Now I take a third order polynomial, basically a cubic. Something of the type a plus bx plus cx squared plus dx cubed. And now I use that, and I use exactly the same idea, right? I use the cubic, I make a prediction, I subtract it from the data given to me on the sine curve, and I find what my fits are. And you can see over here that the population curve is green and the sample curve is red. And they both do a much better job of actually capturing the sineness of the curve. And that kind of makes sense. Can somebody tell me why that makes sense?
There's more room for adjusting parameters when you talk about cubic polynomials.
Exactly. Beautiful. That's an absolutely fabulous answer. There is more room for adjusting parameters. And now we're talking about a cubic. So you're talking about 4 parameters. You can combine these together. You know, you have an x cubed term, so it can go negative as much as you want it to, and you can add that thing in, and then you're all good, and you can get a much better fit. So one of the things that you can see is that as you make this a little bit more complex, and if I had actually taken a quartic or a quintic, I could have probably done an even better job. So the more complex I make my models, the better I can do to fit my data. You know. Now, does that make sense to you? Let's take the sample. I have 20 data points. Can I fit a model on this with absolutely 0 error?
We can.
Okay, and can you tell me what kind of a model would that would be?
A perfect fit.
Yes, but so why would a 20 order polynomial give you a perfect fit? Or actually, it would be a 19th order polynomial would give you a perfect fit. You don't even have to go to 20.
Because it doesn't have any noise in that. So maybe we can get.
No, it has nothing to do with noise.
it's easier to fit.
So does
small
it have
number of
something to do with the Taylor approximation for?
Nope, nothing to do with the Taylor approximation.
Because it matches the data given to us exactly.
Exactly, it matches the data given to us exactly. I can write 20 simultaneous equations in the coefficients, right? With 20 points. And with 20 simultaneous equations and 20 things to find, I'm done, right?
Right.
And so therefore, I can get absolutely zero error if I fit a 20th order polynomial through this. So at this point, you might say, okay, we're done. Go home, we're done. Just fit a 20th order polynomial and you've got the best function. And we'll soon see that this is not the case and why.
Hello.
Yeah.
But that's not possible practically, right? Like that would be overfit, like
but you're
before the
hello.
Yes,
you're giving the answer away very early. So wait. Yeah, people who've taken the foundations program are not allowed to give answers to some of these questions.
Yeah, got it actually.
Yeah,
I knew that.
Okay. All right.
Rahul, I have a doubt.
Yeah, go ahead.
Yeah, so you mentioned that you know the sample that we select actually has a significant impact on the estimating function. So supposing the data is really noisy and then we select a sample which is not really representative of the entire data set, would that like impact these estimations significantly? And
yes, it will. And if you'll wait for like 3-4 minutes, you'll see it.
All right. Okay.
Yeah.
Thank you so much.
Absolutely. But you're absolutely right.
Okay.
You're absolutely and fabulously right. That's totally correct. Okay. So more about approximation, or as I like to call it, learning without noise. So our target, the sign with no noise. We're going to construct a sample from this population. How are we going to do it? We're going to just randomly choose. So if I want to make a sample of 20 points, I randomly choose 20 points like I did here. Okay, that's our game. Okay, now here is what we're trying to do. And this goes to Sukriti, right?
Yeah, Rahul.
Yeah, this goes to your question, right?
Yeah.
In life, you only got a sample and you want to predict. You don't want to predict on the sample. If all you have to do is to predict on the sample, then put that 20th order polynomial and go home. There's nothing to be done. What you want to do is you want to predict on the population. You don't care about those 1,000 people, whether they'll vote for Trump or whether they'll not vote for Trump. You want to know if the rest of the US is going to vote for Trump or not vote for Trump. At that point, you might want to nuke the US after it votes for Trump again, but that's a different matter. So you want to predict on the entire population. Now, as a result, you want your fits to be robust. And this goes to Sukriti's point, that if your fits changed very much from sample to sample, how could you be sure that the results you got on one sample were generalizable? So there's no robustness, you're out of luck. And this theme of robustness of your fits will come back again and again and again. But informally, you can see that one condition for this is that your sample is actually representative of the population. And one way to think about representativeness is to go back, to this orange points over here and see, do they cover the entire range of my X as well? And you might say, yeah, there's some stuff left out below minus 0.8 and above 0.8. But it actually has points everywhere. So, I wouldn't expect it to do a terribly bad job. But this is 20 samples, right? Out of 100. This is 20 points out of 100. There is the possibility that you might get 20 points chosen out of 100. Generally, 20 points out of 100 has a very high probability of being fairly equally spaced. But it's absolutely likely that 20 points out of 100, the 20 points may be all next to each other and on the left of the graph. And then you would be out of luck, as Sukriti pointed out, on the right side of the graph. So you want your sample to be representative of the population, otherwise you're out of luck. So for that reason, you want a sort of large sample. But let's see what happens if you don't have a large sample. Okay, so on this left side graph over here, I took this and I said, I'm going to make samples of 5 points. So I created 200 samples of 5 points. And for each one of them, I fit a line to these 5 points. And these are the 200 lines I got. Okay. So what's your observation about the left side graph?
More condense.
More concentrated.
There is a concentration, right?
Yeah, there's a concentration. It's more precise.
Yeah, it's more precise. Even though I've only used straight lines, the straight lines seem to want to line up with each other. Can somebody explain to me why?
I think it's because the size is greater than relative to the one on the right.
Yeah, but I mean, yeah. So I mean, so it looks like a sample size of 5 seems to be enough to get some good coverage on the sine curve, right?
Yeah.
Yeah. Now look what happens on the right. I've taken samples, 200 samples of only 2 points. Now, if I have 2 points, it's trivial to fit a line, right? You just join the 2 points. But what are the odds of getting 2 points on just the bottom left of the sine curve?
It cannot explain the pattern of the data, or probably the curve. It won't be able to explain that if you just have 2 data points.
Yeah, with 2 data points, it does a much worse job, right? You can see it's hairy all over the place. It's like you didn't comb your hair, right? Or if you have my hair and it's uncombable, it's like that. After 6 months of not cutting it. So it's a very kind of hairy graph out there because you're absolutely right. If I get 2 points on the left, right, I get 1 point over here, and you guys can follow my mouse, right?
Yes.
Yeah.
Okay.
Yeah.
So you get 1 point over here and you get 1 point over here. And then you have all this kind of like, you will fit a line like that. And you can see some lines have been fit like that. And the same thing's happening over here. There is more of the distance of the sine curve over here. So it's still more likely you'll get 2 points over here. So you still get some concentration over here. But the concentration is definitely 5 less, much less than in the 5 case.
But is it like correct to say, like in case of let's say bias sampling also, if we are taking less number of sample points compared to one bias sampling where the sample points are more, so is it correct to say that in case of such sampling where it is biased but sample points are more, overall the curve will be better, like we can get a better predicting system kind of thing?
So that's a complicated question, and let me kind of answer it later. It depends on exactly how that bias happened in your sampling. But that's it's a deep and it's a complex question, and it won't help everybody else right now. So let's take it offline and do it after the class. Yeah.
Yes.
But it's a good question. There's one more question that I want to ask you guys about this. Given that I have only 2 data points over here, should I have fit a line to them?
Not really.
What would have been a better fit if given that I had only 2 data points?
A straight line maybe.
A flat line, right?
Yeah.
Yeah, because it's only 2 data points. Just average the y's out there and give that as your answer. So I think one thing you should realize from this graph is that if you're ever doing any kind of fits, it doesn't depend on how complicated your target is. The target out here is a complicated sine curve. It depends on how much data you have. The complexity of the model you can choose depends on the amount of data you have. So here, because I had 5 points, I can do straight lines. I'm okay. But here, because I had 2 points, straight lines just look very ugly. If I had just done a flat thing over here, then I would have got a much closer band in the center between the between the 2 peaks of the sine curve. Okay, so that's a good thing to think about. So I'm happy that you guys are answering these questions correctly, because that means that you have built up a kind of good intuition about this subject, and you have some natural ability with it. So that's good. Okay, so now let's do another example over here. Actually, you know what? This may be a good point for like a 2-3 minute break. So if you have any questions, please ask.
I haven't got any.
You go ahead.
No, I haven't got any questions.
Okay, anybody with any questions? If nobody pipes up, I'll go on.
Yeah, I have a question.
Yeah.
So we spoke about the degree, right? Like power 5 raised to power 20. So how do we decide what number do we stop at?
Aha. That's the story for the very last slide if you get there. But I'll get there.
Okay, thank you.
Yeah. Okay, so let me do another example. So consider a very simple scenario in which the probability of voting for Romney, so this is from the 2012 elections in the US, is a function of how religious the population in a county is. Okay, so this is the fraction of religious people. X over here, between 0 and 1 is the fraction of religious people. And this is a fraction of the number of people who said they would vote for Romney or who would vote Republican, but specifically Romney in this case. This is completely cooked up data, by the way. But I'm just sort of like saying, trying to motivate this problem. YI is the data that pollsters have taken when they tell us their estimate of the fraction of people voting for Romney, and XI is the fraction of religious people in county I. Okay, so let's assume we have a population of 200 counties, and notice one thing about this population of 200 counties. There seems to be a somewhat higher sampling between 0.6 and 0.8. So this is not uniformly sampled, right? There's like more counties between 60% religiousness and 80% religiousness. Probably fairly representative of the US. So that's the setup of the data set. And we're going to take a sample from this data set. The data set right now is colored in red, and the sample is taken in these blue squares. And you can see these samples. This is actually a reasonable sample of 30 points. It's also a little bit more crowded between 0.6 and 0.8 over here. Okay, so now pretend these red dots are taken away. So we're not told anything about the population, right? We're not told anything about this generating function. I haven't told you how I generated this curve. It's some curve. And I'm not going to tell you how I generated it. You don't know about it. And you're only left with the blue squares. The red stuff is gone. And now your job is to look at these different hypotheses belonging to these different hypothesis sets. Straight lines, cubics, quartics, quintics, 20th order polynomials, 30th order polynomials, 100th order polynomials, and see which one of these does the best job, right? That's your task. Everybody okay with the setup of this problem? Any questions?
No.
No. Okay. So usual, right? We'll first try the straight lines. So I fit a straight line. I find the best fit straight line. It turns out to be this orange curve. Do you think this orange curve could ever look like the data, even if I gave you 1,000,000 points of data?
No, sir.
No, right? It can never get the curve, right? It's a straight line. So this is called bias or misspecification error. Okay, so keep that in mind. That happens when you've used something which does not have enough flexibility to capture the data. Okay, so we first try a straight line, doesn't work really well. Okay, now we try a 20th order polynomial. As somebody pointed out, it has a lot of parameters to wiggle, and because it has a lot of parameters to wiggle, it can fit this data really well. And this is the best fit amongst 20th order polynomials, right? So this is the game we are playing. We're taking every such hypothesis set. Here we took the hypothesis set of straight lines and said, what's the best fit straight line? And that was the orange line there. Here we take all 20th order polynomials, not 19th order, not 18th order, not 17th order, the way we've organized this, but just 20th order polynomials. And said, okay, do a fit. And does it seem to do better? It does, right? So, sample of 30 points of data. Now I'm not showing you the population at all. Which fit is better, the line in the hypothesis set H1 or the curve in the hypothesis set H20?
Curve in the hypothesis H20.
The curve in H20, right? Yeah, super. I'll plot the squared error, and it basically, here's what I didn't plot the square error here by adding it up over all the points, but I just plotted it at each and every point in the population, right? And I said, what does that look like? And you can see what it looks like, by order of magnitude, like literally, the error for the blue curve, the blue error over here, which is the H1 error, is, or the error when you use G1 to do the fit, is of the order of 10 to the minus 2 to 10 to the minus 6, and this is 10 to the minus 14 to 10 to the minus 30. So the 20th order polynomial is doing much better. I would like to sort of like, emphasize what I'm kind of doing over here a little bit, because it may help understand. What I'm doing over here is I'm saying that I am looking at all straight lines, and all straight lines, so all functions of the type h1 of x, and the best fit straight line I'm going to call g1 of x, okay? And then I'm going to look at all 20th order polynomials, i.e. all functions, sorry, not g20, h20 of x. And I'm going to find the best fit out of those, and that's what I'm going to call g20 of x. So that's my notation throughout. In general, I'm going to call hypothesis function H. The best fit hypothesis function is going to become G. And then f of x is the function that actually generated the data. Okay? Are you done with the notation?
Can you again tell us how do we interpret, what do we interpret from this plot of squared error?
So from this plot of square error, you're seeing that the 20th or the best fit 20th order polynomial, G20 of x, right? The best fit one. Remember what I'm doing to get this fit. I'm taking all 20th order polynomials and asking which 20th order polynomial minimizes the squared error. You with me on that?
Yes.
Yeah? Okay, so it turns out that, and I showed it to you on the previous graph, there is a particular, I need to get rid of my annotation toolbar to be able to do this. Right, it turns out that there is a particular 20th order polynomial which does that. Let's call that G20 of x. Okay?
Okay, okay.
This is the error that G20 of x has with respect to the data.
Yes.
Except that what I've done is because I have the population, I've taken the data on the entire population to show you this. Yeah?
Right.
Okay. If I didn't have the population, which is the case in the real world, right? I would not be able to show you this graph. Make sense?
Yes. Good.
Yeah. Okay. The annotate toolbar out, clear all annotations. Okay. Let's kill the annotation toolbar. Super. So one of the questions is, how do we generalize from these samples over here to the population? As I told you, I could not show you this graph. And I've shown you the situation where I have the 20th order polynomial doing a much better job than the straight line. But how do I generalize from sample to population? This goes back to the question is, how do we make good predictions, right? We want to predict on the population at large. But the conundrum is this. We have not seen the population. If I had seen the population, I would say, well, minimize the risk on the population, minimize the error on the population, right? That's really what I want to do, but I can't do it because I've never seen those points. So what's our strategy out here, right? So strategy is that is something we've already done over here, right? We've minimized the risk on the set of points we have, our sample. And using the sample, we found our G functions. And once we found our G functions, we're starting to hope. We're saying, okay, once we have found our best fit model G, let's just hope our risk does not change out of sample or when using a different set of points. Now, as engineers and scientists, is hope good enough?
Never.
No, right? It's never good enough. We need to actually show this. We need to figure out how to do this. So that's what's going to be the second half of this talk on how we figure out how to do this. The one parenthetical remark I want to add out here is that if your sample was just somewhat representative of the population at least, right? If it was large enough and therefore had a greater chance of being representative of the population, our hope in B is more well-founded. And if it's not, like it wasn't in the sine curves I showed you over here, then it's not very well-founded. Okay. And that's the question of how representative is our sample, right? Okay. So then this is the statement of our learning problem. This is what we want things to happen. We want to find the error, the function G. Yeah, go ahead.
Before we proceed. I mean, why are we even bucketing them separately, like H1 hypothesis being the linear ones and H20s being the separate degree? And can't we even include that degree in the parameters that we are optimizing over? Like,
yeah, you could. How you organize it does depend on, yeah, you could absolutely do that. Why are we organizing it in this fashion? If you try and take too large a set, you'll overfit just by having a lot of functions in it. What will end up happening is randomly, so this is somewhat of a subtle and complex point, but you'll just by having terribly huge numbers of possible functions, randomly one of them will fit. And then once you look at it on the population, it won't do such a good job. So it's an overfitting problem. We can talk about it a little bit more later because it's a really subtle overfitting problem. Yeah?
Rahul, so what you're trying to say, Rahul, so what are you trying to say here is, with regard to this question, that if we if we try to fit a model on the sample, it may or may not necessarily be that it'll fit on the population that perfectly, right?
Yes, and that's the problem we need to deal with, and we'll see examples of this problem very soon. Yeah.
Okay, thank you.
Yeah. But I wanted to make the statement of this kind of learning problem, right? How we are learning models. I want to make the statement of that learning problem. And the statement is part A, this we know, that on our sample, find the G which minimizes, right? Inside a hypothesis set H, find the G which minimizes things for us. Then once you've done that, hope, that's part B, that the out of sample or population error, which I'm calling as R sub out over here, is roughly the same as the small one we found on our sample. So if the sample is representative of this population, this has a chance of being true, but we need to ensure this, right? And that's what we're going to do in the next part. Okay. So one thing I did is I said, okay, I made this prediction on our using our sample points. Let's see how well the prediction does on the entire population. And in this case, it actually does a bang up good job, as you can see. Kind of makes sense, right? Because it's actually producing the curve back very nicely for us. So it's doing a very good job on the rest of the population. Okay. Okay, so that's a good place to stop and ask some questions of you guys. So normally, if we were doing this in a class, there would be kind of exercises. But since I didn't have any of you, log on to the site before, we didn't put up exercises on the site. So this would be a good sort of like point to, to talk to ask a few questions. So my first question to you over here, and just basically just shout out the answer. Unmute yourself, shout out the answer, mute yourself back, right? So my first question to you at this point is, how do we find the best fit function on our sample?
By minimizing the errors.
By minimizing the error. Okay. How does the likelihood that we will get a best fit function change with the size of the sample?
The greater the sample, the greater the size of the sample, the greater our accuracy.
Exactly.
Function.
Exactly. What's the problem with extremely low sample sizes as we saw in the sine curve?
It may not be representative of the population.
It may not be representative of the population. Thank you. So, okay. So I think you've got the three salient points out of this, okay? So what we did so far is we've talked about the theory of approximation, right? There's no noise in this scenario, right? We just have a curve and we're trying to capture it by another curve. We have a curve. Somebody gave us the curve. God gave us this curve. Then God hit us on the head with a hammer and said, okay, go to sleep. 20 years later, we woke up and we said, I don't know what this curve is. And I'll try all kinds of things. I'll try lines. I'll try 20th order polynomials and try and see what does a good job. And in this case, we found the 20th order polynomial. That's good. Okay. So Siddharth, are you here at this point or not yet?
Siddharth is here.
Yeah.
Just a second. He's
I
joining.
think you wanted me to stop halfway through and.
Yes.
Hey Rahul, I'm here.
Yeah, go ahead. 5 minutes, eh?
Yeah, just wanted to make a series of announcements, everyone. This is, though my video is not live, my name is Siddharth Das and I'm the CEO of Univ.AI. Just wanted to, I see that many of you also attended the last session that Rahul did. So they are, I guess, so some of you will hear this twice over. But a couple of things, I just published a Telegram link. Let me do that all over again. Or if you just scroll up slightly, you'll see that. So this is our public channel where when people ask us questions, we answer as well as provide updates to our project research and other program initiatives. So as time rolls on and our next class starts, right after, you'll start to see announcements for research, starting with computer vision research with Achyuta. We'll also have a series of project opportunities come up, especially for those of you who are up on the learning curve and have some of the skills that we seek. We have, at this point, 3 or 4 different project initiatives which are live with various clients. And some of you who are are already accomplished in some aspects of machine learning can actually participate with us on that. So that information is coming up as well. And new programs. We are still thinking, evolving, and figuring out what's the best way to provide this learning. So that's also coming up, right? Share the link while we'll send you summaries of this session as well as other stuff. Join this. That's the best way to stay in touch in case you want more information about us as we move forward. Second is that we have 2 or 3 different scholarship and financing initiatives that we have launched for those of you who might be interested in joining our upcoming class. One is for those who are high achievers and have evidence of that, which means academically accomplished, tons of prior experience in machine learning. We are happy to offer you some form of tuition assistance to join our programs, especially if you need it. And so that's a general scholarship for everyone. For all women, we offer some tuition assistance or the other. That's called our AI Women Scholars Program. Go to our website, to the homepage, and click on the home banner right now and check it out. It's a structured program where we intend to provide not just tuition assistance, but a variety of mentorship initiatives to ensure that we provide a really outstanding learning experience specifically designed for women. And that's being led by many of the women in our team who some of whom are actually here on this session. And the last one is something that we are sort of fine-tuning, but it's available right now, and that is an income sharing agreement, which has a small partial upfront payment and the remainder via an income sharing agreement for those of you who are interested in taking our programs but want to defer most of the fee payment to when it is financially comfortable. So those are the 3 things that I wanted to say, along with our Telegram group. So that's about it, and we'll post this again toward the end of the chat. So that's what I wanted to share with you. And if anyone has any questions just right now before Rahul starts up again, I'm happy to take 1 or 2 questions.
Siddharth, we have a question on chat from Harshvardhan Rathor. Can I still participate in live projects even if I'm not enrolled?
Yes, everyone can. And I think when we do it, we will solicit application. Both the application and the selection process will be quite rigorous. You will, and there will be fairly strong commitments. So I want to also communicate to those of you here that as this system rolls forward, any of these research or participation opportunities in live or otherwise not live projects will be strictly on a professional basis, right? And therefore need to be treated as such. So short answer, yes, you can participate if you're not enrolled, and there's a process for it, and will depend on both what your situation is right now as well as what your qualifications are. Yes, Rishikesh, further information on ISA is available on the website. It's kind of being changed right now. I don't know if it is in its final explanatory form. What we had so far was not very clear. So I think we are publishing some new criteria like cutoffs, end of commitment, start of commitment, all of those things. But in case you do want to, again, join the Telegram channel, fire your questions there and we'll answer. There is no link for the merit scholarship, Vinayak. Yeah, and it's under financial assistance on the homepage. You need to apply for the program, take a somewhat, it's not so quick exam. It's just a situational assessment test with no particular syllabus. We test your skills in Python, NumPy, and basic mathematics, statistics, linear algebra. And then based on how you fill out your application, we talk to you and then make you an offer. So so fill out an application with as much detail as you can, especially in the long questions. Take the test and we'll go from there. Shreyans, there is no link for live projects as yet. Like I said, join the Telegram group and we will announce it as it comes.
Okay, so shall I take back over?
All right. So I think, yeah.
Okay. So while we are here, I think what I'm going to do is firstly not have my Zoom split across two screens, which is driving me absolutely nuts. Get back here. Stop this share. And I wanted to show you a little bit about our platform, which you should be able to go and see this course on. There are some rough edges because I just put the course in today, but they'll be ironed out. And the video feed for today's course will also be put in over here so that you can actually see it. So it's at courses.univ.AI /TEOL. And there's a table of contents to start with right at the very bottom, and it's divided into sort of like two, if you like, sections: learning a model and finding the right model. We are right now within learning a model. And we have 3 chapters over here, and we right now just finished noiseless learning. So if you just click on noiseless learning, we can go in here. And you can see what you have over here, what you learn. And I split the slides up into sections so that you can see them in a somewhat more easier fashion. And there are slides over here, and you can just move on these slides. I think the right arrow key will move you. And you can see all the slides. But what I do actually like is which is a much nicer feature of this is you also have notes that are very detailed notes, including the Python code that was used to generate each and every one of these plots that was there. So even if you didn't know Python, you could actually probably learn Python from just going over this course a little bit. So each and every one of these plots, and there are some more stuff because you don't want everything which is in your notes to be on the slides over here. And then in every such page, there is a takeaway at the end. So if you press for time and all you want to know is like, what should I have known reading this page? Go to the bottom and read it out. The top of the page has this little piece which tells you what you learn over here. Now, one final thing I wanted to show you over here is that if you move this little collapse doodad to the left, you'll see a little pin thing show up here. And when we put the videos, they come right next to these slides, and they also have a pin, and you can pin the slides and the videos together. And if you pin this, it pins the content to the side. And then as you move the slides, we'll take you to the exact point in the code where in the notes where the notes are corresponding to that slide. Well, it's not exact because we're not doing it on a slide to section basis, but it's every few sections. And you can actually move the notes as well. And as you move the notes, your slides will change. So as you're moving down in this, your slides will change depending upon where I've set up the breakpoints. Okay, there we go. Finally, you can click this little thing, which is a full screen mode. It has a shortcut F, or you can click the box, and you get the slides in full screen mode. So you can focus on just the slides and not worry about the notes. So it's a nice little system. Once the videos come in, they synchronize as well. If you move on the slides or if you move on the notes, they will take you to the point in the video corresponding to the slide. So hopefully you'll find it useful, to learn this stuff. Okay, so enough about that. Let's go back. Share screen. Find my slides. Where are my slides? Where did I put my slides? Here they are. Okay, sharing is paused. I think I need to go to the correct screen. I am screen share. Right. Where is my screen? Here we are. If you are where I am, you should be seeing prediction on population good. Is that where you are?
Yeah.
Yeah, okay. Okay. So The real world has noise and finite samples. Usually both of these together, mixed up. So you're in a bit of a pickle because you got to deal with all these problems. So here's, a little toy example. Here's what this looks like. Here's my generating function f. Here's my in-sample y. So it's my observed y. These are the samples we saw earlier. We didn't see that actually. We saw the population there. Oh, no. I'm getting a little bit confused. Sorry, my bad. What I've done out here is I've added a bit of noise. The blue squares out here are the sample, but the samples we had earlier, but with some noise added. And the orange dots over here, the orange circles or dots over here, are the population with some noise added. So it doesn't look as clean as this, right? Because now it's all over the place. The red things are the orange things, and the blue things that remain the blue things. But they sit all over the place. Okay. Setup of the problem clear? We now have noise. We still have a sample, we still have a population, and we're going to try and predict from our sample. So far, so good?
Yeah.
Okay. Yes. Where does the noise come from? From many places. So here's an example. Suppose I had 2 counties, and each one of them had 80% of self-identified religious people. Now, on historical trends in the US, if the first county, if 2 such counties, both around 80%, if the first county was made of mostly white people, you'd find that the fraction of those claiming that they would vote for Romney is much larger than in the second one, if the second one is mostly black people. So in that case, race is a much more important predictor. But if you're not predicting versus race, you wouldn't know this. And so you would get some very noisy Y's next to each other. So one may be very high and one may be very low. So you'd get a situation like this where one was over here and the other one was, the next one was right down there. Okay? So that's what noise does for you. So in other words, we now have a noisy target Y, which is our generating function f of x, which we don't know. Nobody told us. God hit us hit us with a hammer and said, haha, I'm not telling you the generating function. But that's what we got. And we want to approximate it using some function g, which is taken from some hypothesis set, maybe H1, maybe H20, maybe something else. So far, so good? You get what we're trying to do?
Yeah.
Yeah. Okay. All right. Here's my fit using H1. Okay. So I do it on the I do it on the sample, and it's the one with the big blue squares, and it's plotted against the dashed blue line, which is what happens when there was no noise. Now, do you see much of a change?
No.
It's still bad, right? It can't capture the curviness.
Yeah.
So you're like, okay, I'm going to go to my 20th order polynomial to try and do this. Okay, so you go to your 20th order polynomial to try and do this. Okay.
Overfitting.
Yes, but then you may not use the word yet. Anyone who uses the word overfitting must wash their mouth with water. Now, that's what my 3rd standard teacher had told me back in school, because I had said a bad word in class. Well, overfitting is not a bad word here, but still, no overfitting until I write it, right? Don't say that. So what's happening out here?
We can say over.
You can say it to yourself. So what's happening here? Can somebody explain why this blue curve is going all over the place?
It's trying to capture each and every point in that.
It's trying to capture each and every point. It's got these 20 coefficients or 21 coefficients of wiggle room. So it's trying to go through this point over here. It's trying to go through this point over here. It's trying to go through this point here. And it's trying to go through this point here. And the only way it finds out of going to this point is to go really, really, really high and then come back down. And then get that point and then go really, really down and come back high and get that point. Where does it do a much better job?
In the center of the curve where we have more data.
Exactly, in the center of the curve where we have more data, right? So it does a much better job in the center of the curve where we have much more data. So that's definitely the case. Okay. Now look at this versus the population. And you see how bad it is versus the population. Over here, at least it tried to get all these points over here. It tried to get these blue squares over here. But can you see how bad it does, especially over here, for example, with the orange points? No good, right?
Yeah.
Yeah. So this exactly is overfitting. This best fit G20 has overfit to the sample. Okay. This overfitting is just a fancy word for it's actually fitting to the exact points in your sample. And if your sample is even mildly weird, then you're in, or not representative, you're in trouble. But even if your sample is representative, if you construct a model which has so much wiggle worm space, 20 parameters to wiggle all over the place, you will try and fit to those exact points. And you might get into trouble on the other points. So the takeaway lesson from this is that we must ensure that our model does not fit the noise. And in fact, now H1 is a much better hypothesis space. If I do the same graph I did earlier, the blue one is G1, and the orange is G20. The new G1s and G20, the new best fit line and the new best fit 20th order polynomial. And notice what happens. There is a place that the polynomial does a little bit better, and that's in the middle. And in fact, there are all these undulations where the polynomial goes down very fast. Can you guess what's happening at those points where the error becomes extremely low?
I think that's where there's a lot of concentration of data.
That's where there's a lot of concentration of data, or that's where you have your sample points and that kind of stuff, right? But you go even a little bit away from here, boom, and it becomes comparable to the blue curve, and boom, and it becomes worse. Okay? So how do we systematically decide what is underfit and what is overfit? How do we find a hypothesis set then of the correct complexity? This is the problem that we want to solve, right? So the plot provides us a hint over here. What is the hint that the plot provides us? We just said it. You just said it. At points where there is a lot of concentration, the error is low. But at points where there are not so, but at other points like this one here, where you don't have the samples. I have, by the way, put all the samples we had in our all the points in our sample. I've shown with these pinkish reddish lines going down. So there are no points near the sample. What's happening? Can somebody tell me?
There's high error, I guess.
The error is high. So if I can somehow fit at points not on the sample, not in the sample, I would be able to diagnose this problem by looking at the high error. Does that make sense?
Can you repeat? I didn't quite catch that, sir.
So if I was somehow or the other able to get some other points which were not inside my sample, like a point like this, where my mouse is,
yeah,
I would be able to diagnose this problem with G20 because the error would be extremely high. Does that make sense?
Yeah.
Okay. So, am I not stuck though? All I have is my sample. I don't have the population. So can anybody come up with a strategy to fix this?
At the extremities, like you are working on the most extreme points. Mm-hmm. So you just have to look at them, because in the dense part of the data, both the curves are performing approximately the same. So why do you need more points where we are missing them?
Because you want to make a prediction all over the function, right? All over the range of the function, not just at the points where you have data, right?
Reduce the degree.
Yes, sir. Can we reduce the degree? Maybe like, because we can see if it is G1, we are getting a kind of graph, and G20, we are getting a different one. So maybe somewhere like.
No, somewhere in between. No, I totally get where you're going with that. And I think that's actually a really good idea. But, you know, so 2 points over here. I think Maitri, did I get your name right?
Yes, it's Maitri.
So she's making the point that why on earth are we trying to predict out here? There are no samples out here. So there are 2 reasons to do that. One is that you don't know that any other sample may not have had samples here. If it was like way to the left and way to the right, you know, you might say, okay, that's not within our range of prediction. I don't care about it. I'm not going to predict over that. In fact, you might say if you only care for counties between between 55% and 85%, this is good enough. You could even take the 20th order polynomial, go home, and you'd be right to make that statement. But you can even see these undulations over here, right? So if you look at this one, where my mouse is, extremely low error here, and the error suddenly popped up. So it's like I take an infinitesimal step over to the right, and my error suddenly pops up a huge amount. It's not behaving in a very robust fashion. Does that make sense?
Yeah, it does.
Yeah, it's not being very robust. So that's kind of like a bad thing. When you have, when you're trying to predict things and things are not robust, then you should really be worried about your predictions over there. So the question I'm asking you though is, based on this notion that if I go even a little bit away, the error becomes that high, how might I construct, and given the fact that you don't have a population, how might you construct a mechanism to use this large error to diagnose that this 20th order polynomial is a bad model?
So Rahul, I think one of the ways could be to just take multiple buckets of these samples, like randomly selected buckets, and then iteratively see if across all those smaller buckets, what the error is like.
What the error is like. So what you're saying is basically carve out a smaller bucket.
Yeah.
Yeah. So that's exactly it. That's exactly the idea. And what Sukriti described was actually the even more complex form of it, which is called cross-validation. But this is exactly the idea of what she said is you take your sample, you split your sample into a training set and a randomly chosen validation set or test set. So instead of adding, because we have no capability to add because we have no new data, we subtract. We say take something away from this data and keep a little bit of that data out and then see what the error is on that. And Sukriti's, I think, very good idea was actually taking buckets all over the place and look at those buckets, because that'll give you an even more robust answer. Okay, so absolutely. So that's the way to do this. Now I want you to, so one more question. So I'm sorry I'm peppering you with so much questions, but it's kind of fun to go in a question answer sort of fashion. Now it must have dawned upon you that you're taking your already small sample and making it smaller by doing this.
Yeah.
Based on your knowledge now from seeing that sine curve example with 5 data points and 2 data points, what kind of a model will this force you towards?
A not so generalized one.
Pardon me?
Not so generalized one.
Is it a not so generalized one, or is it a, think about what we did there, right? We used a straight line for the 5 data points and we used a straight line for the 2 data points. Which one was worse?
The 2 one.
The 2
It
one,
would
right?
not explain the data set that that well.
Okay, so it may not be able to capture the entire data set that well. So is it a more complex model or a less complex model you're being forced towards?
Less complex.
Less complex model, right? Exactly. And that in this situation may be a good thing, because you see that G20 seems to be too complex. It's doing these undulations. It's going up and down. It's going all over the place. Yeah? Did that point become clear?
Yeah.
Okay. Okay. So just for fun, I'm going to do that sine curve thing again. So I'm going to take 200 samples of size 30 from the population and fit a straight line and a 20th order polynomial to each one of these. And I'll plot them all in one plot. And even before you see it, I want you to guess what the plot's going to look like. So first, let's talk about the straight lines. I'm taking 200 samples of size 30 from our population, and I'm going to show you all the straight lines. Are they going to be all over the place?
They're going to be all over the place and not.
Or are they going to be more or less pointing in the same direction?
They'll be all over the place for a straight line and not concentrated around the straight line.
How about for the 20th order polynomial?
It could be concentrated around the the line that the 20th order polynomial creates.
But the 20th order polynomial, remember, is not a line, it's a curve.
Sorry, the curve.
Okay, let's see if this is the case. So I think you got it exactly the opposite. But can somebody explain what's happening on the left?
It's not generalizing the whole population so well.
No, it's it's not a question of not generalizing. So which do you think is a better generalizer, the one on the left or the one on the right?
Comparatively, the one on the left.
The one on the left, right? So it's actually generalizing it much better. It's not generalizing in the sense that it does not get you the curviness, right? But remember, you never see the red curve. You only see the orange points and the blue points. So the population is the orange points. I would argue that all of those curves are actually doing a good job of going in between the orange points. They're not doing terribly good job, but it's giving you the rough idea of going from the bottom left to the upper right, correct?
Yeah, correct.
So in that sense, all the predictions, all those 200 models are much more robust. But having said that, I will never capture the curviness of the red curve, right? So that's my bias. So that's my bias limit. I mean the bias side of things by doing that. Okay. What happened on the right? This looks like a really, really, really bad hair day, doesn't it?
It's a very sensitive model. Right?
It's very sensitive. Every time I change my points a little bit, it goes off in some other place. And that's why I get all this hair over here and I get all this hair over here. And only over here, when I have lots and lots of sample points, lots and lots of blue points over here, and lots of population points, lots of orange points. Therefore, every sample I create is likely to get more points from here, that I get a much more tighter fit out here. But wherever I have less possibility of getting samples, I do much worse. So in other words, I'm taking this and repeating it again and again and again with different samples, different randomly chosen samples, and getting different curves over here. So this sort of illustrates to you how bad this 20th order polynomial is. Yeah? Yeah, there was a question. Go ahead.
Is it also because, so can we say that the sample is not really a good representation of the population because it is so widely spread out over the curve?
So that's a very dangerous statement to make, and I'll tell you why it's a dangerous statement to make. You are choosing 30 points out of 200. Likelihood is that, you know, with choosing as many as 30 points out of 200, you'll get a good spread all over the curve, right, of these points. You're absolutely right. There'll be some of them for which you don't. And then that's coming because your sample is not represented. But there is a second part of it, which is at play over here. So the first problem, which you very nicely stated, is that the sample may not be representative. But the second problem is that you've tried to fit a model that is so complicated that it's actually fitting to the noise on any one of these samples rather than the signal. And because it's fitting to the noise, it's giving you these highly undulating curves. It's giving you multiple such curves, right? Multiple such curves. And when you look at these multiple such curves, you have no predictability left. Because on one curve, it might be over here, and the other curve, it might be there, and the third curve, it might be down there, and, you know, all kinds of stuff. In fact, perhaps a nicer way to see it is in this graph over here. So here's what I did is I took all the coefficients in my 20th order polynomial and all my coefficients in my line. That is my second order polynomial, my best fits. Okay, all 200 of those because I did these 200 samples. And look at the, I can't even show you as compared to the other polynomials, all the possible values I get. But just look at, for example, coefficient 2, which is the coefficient of the quadratic. It ranges all the way from 10 to the minus 10 to the 10 to plus 10 to the 10. 10 to the 10. Right? That's roughly like 10 to the 3 to the 3. So that's roughly speaking a billion. It's going from a billion to a minus billion. Do you expect to have a stable polynomial with such high coefficient values?
Not at all. Not really.
Not at all, right? So that's exactly what's happening here. That each time I just change the sample slightly, and boom, I get a completely different fit. Not predictable at all. Not robust at all. Bad, right? Okay. So let me come to the last part then, in the last 5 minutes or so, or 5-6 minutes that we have over here, and talk about how are we going to do it. And you guys just told me how to do it. Keep a held out set. Take some part of the sample and leave it out. Okay, so I don't have to say much about this because you told me what to do. High sensitivity to samples is a very bad sign. You can get larger samples so that they're more representative. You can fit simpler models, and really, typically, it's a combination of those two things you're doing. And remember, that the complexity of the model you fit depends upon the size of the data set you have. So if you're going to take some data away by keeping a holdout set, you'll naturally be forced to a more simple model. So that was that example again, right, of the sine curves. Okay. So now this comes up to the final part of our talk, right? This idea of model comparison. We've been postponing this to the end because we didn't have a strategy to do it, but now we do. I forget who, but somebody said over here, why don't we choose something which is not as low as 1 and not as high as 20? And you're absolutely right. Because 20 is too complex, 1 is too simple. It's going to be something in between. But how are we going to fit it, right? Well, let's go back to our ideas, right? The error must be smallest on our sample. And we've talked about interpolation, right? Where we actually just, use 20 points and use a 20th order polynomial. And then you'll get exact fit, you'll get completely zero error, and you can't do anything. And then we talked about the fix, which is to leave a little bit of the thing out and check the error on that little bit of thing you left out, which we'll call a held out set or a validation set or a test set. Okay. So that takes us to the part B, right? Where we want our out of sample error to be roughly the same as our in sample error. But now, with this idea of taking the small little set out, if that small little set can be a proxy for the population, right? Then I can actually calculate the error on that and say, well, that error is very similar to the error on the sample or whatever is left of the sample, and then I'm good. So do you get the idea over here? The first part is, well, take the part of your sample which you're going to train on. We're going to call it the training set. Train on that set, get the best fit, and then look at the error. That's A. B is whatever you left out, which you're going to call the held out set, the validation set, or the test set. Calculate the error on that and check if it is roughly the same as this or not. If it is much higher, is that a good hypothesis? Hello? Anybody?
That will be overfitting, I guess.
Yeah, it would be overfitting. The error is much larger, which means that, any attempt at generalization has gone bad because my error has become extremely large. My polynomial has gone off somewhere towards infinity, right? Yes, the model should not be too complex, or a small perturbation in coverage going from the sample to population will sink us. Okay, so let's do this. So this is how we're going to do it. Here's the schematic for what you've been saying. We're going to hold out some data called the test set or validation set. Leave the training data out. So here's what I did for my 30 points. I have 1, 2, 3, 4, 5, 6 green points which are left out, and I have 24 points now. So instead of fitting on 30 points, I'm going to fit on 24 points. Find the best fit model, calculate the error of that best fit model on the 1, 2, 3, 4, 5, 6 points. Sum the squares of the errors and divide by 6. This is what I'm saying making sense?
Yeah.
Yeah? Okay. Then what am I going to do? I'm going to do this for each and every hypothesis set, right? I'm going to take lines, quadratics, quintics, hextics, seventics, whatever, I don't know what you call a 7th order polynomial. And then I'm going to tell you on these 6 points, what's that error for each and every one of these degrees of polynomials. Make sense?
Yeah.
And I hope you're getting this kind of notion out here that the degree of polynomials sort of is a proxy for the complexity of the model, right? With the higher the degree of the polynomial, the more complex it being. Okay. So the held out, so now the next part is what we were saying, is that the held out set is going to be a proxy for the population. One can show that this is actually good. This is actually true. One can show that the error on the held out set estimates the population error. But it turns out that this proof is actually not that easy, but it's doable. But it's not surprising because the held out set is just another sample. And hopefully it has the variability that the other samples have.
Rahul, can I ask a question?
Question? Yeah, go ahead.
So for example, if we are testing out different, different functions probably, so one of them might fit the, the held out set that we are testing upon. and the other one might not. But if we compare, just in the real world scenario, if you look at the population, what if, let's say, the 20th order polynomial fits the population much better than the first order polynomial?
So is it possible that a 20th order polynomial will fit the population better? Yes, it is. It though is unlikely if your sample is large enough. And if you did what Sukriti said, which is to take multiple buckets of multiple samples and average over the sample, something called cross-validation, it's very unlikely to happen, right? Because you've chosen these multiple buckets all over the place. With any one bucket, you're absolutely right.
Okay.
Yeah. So if you want to learn more about all this, AI1, which Pavlos is going to do in a few days now, well, a few days being something of the order of like a month, on September 15th, actually goes into this in a huge amount of detail. It does a lot of stuff on validation, cross-validation, all of these kind of things. In this kind of introductory lecture, I really don't have the time to do it. Otherwise, I could have. But so there's this idea of validation, but you're absolutely right. If you wanted even that to be robust, average it over multiple validation sets.
Yes, that is what I was thinking.
Yeah. Absolutely. Thank you. Very good point. Okay. So we're using now this held out set to be a proxy of the population, though we should actually average it over multiple held out sets. Thank you for bringing up that point. Okay. So now we're going to evaluate the error on held out set. So let me just repeat the process so it becomes blindingly clear what we're doing. For every polynomial degree D, we are minimizing the training risk. So on the sample, which is what is left over after taking out the held out set. So we are fitting a model for each hypothesis space, H1, H2, H20, H21, and we are finding the coefficients which give us the best fit model, right? Then we are evaluating the error on the held out or validation set. At some point, you'll see that what's happening is because your polynomials are going up and down and up and down and up and down and behaving completely crazy, you're going to see that this validation set risk on this held out set starts going up. This error starts going up. And you see that happening around maybe about a degree of 11 or 12, and it just starts going up. By the way, in case you want to see how bad this is, the Y scale is a log scale here. So like over here at like this, it's like 100 times worse than it is, well, not even 100, 10,000 times worse than it's over here. Just so you know, this is on the log scale, this is not on the linear scale at all. Okay. So what we're doing now is we're looking at this side. So should I choose any model where this is going up?
We can't.
We can't, right? These are not robust. So it seems that there's an area of robustness which goes somewhere between a degree of 11 and a degree of 1. And maybe it's kind of actually even better over here. Sort of between a degree of 6 and a degree of 1. Any one of these models would do a reasonable job. Up to like 6th order polynomials would do a reasonable job of capturing this data without a huge amount. Turns out that the exact minimum is at d is equal to 3, but that's not really the most important thing because these things are so close to each other. So look what's happening, right? We wanted to minimize the error on this blue set. But as I've told you that, by the time you keep going down and down and down further to the higher and higher order polynomials, this is going to go towards 0. Makes sense, right? Because I can always interpolate at some point. So that's not useful. It's not useful to be here just because it's 0. But then we hit upon this idea that we are actually going to calculate this on this held out set or this validation set. And what do we want on that? We want it to be as close as possible to that on the training set. And you can see it is close until it starts diverging. And here is where it starts diverging around 6. And so where it kind of converges very closely is out here. It converges reasonably closely out here too, but that may be a little bit of a red herring. But you could actually, because doing a polynomial of order 0 may not be the best idea. The error is already high. So you want the error low, which is here. And you want the two errors, the orange error and the blue error, to be kind of the same, which is here. So it satisfies our two conditions. And that's it. That's how you evaluate every freaking machine learning model. There's really no more to it. There's more complicated ways of doing it, much more robust ways of doing it, like cross-validation. But this is the basic idea. And this is the famous complexity plot. As the complexity of your model goes up, find a sweet spot, which is given to you by this kind of red line over here. which is a balance between overfitting, where you're having too complex a model, and underfitting, where you're having too less a complex, too low complexity a model, where the training error is low and the test error is also as low. Now you can notice up here, as you go to the left, you could actually make the difference between these two less, which is our second point. But if you did that, then the error would be still a little bit higher, and that's not what you want. You want the error to be as low as possible. Okay, and that's it. So I went over a little bit by about 5-6 minutes. Sorry for that. But that's really all there is to actually evaluating machine learning models. And every machine learning model you do, whether it's a linear regression, logistic regression, deep neural network model, there will be some kind of notion of complexity. And you will try and figure out how to deal with this complexity by finding out the sweet spot. Now, one thing I didn't talk about, and Pavlos will talk a lot about in AI 1, is regularization. And regularization is this kind of idea where what you're doing is you're taming these coefficients. You're letting your model be as complex as possible, but you're taming the coefficients to be, to not have those high values, and you do it by imposing some additional penalties. And in the regularization is used a lot in deep neural networks using techniques such as batch normalization, dropout, and weight decay. But that's, of course, a topic for a totally different day. Okay, so let me stop there and take questions.
Rahul, the question is if you want to fine-tune your statistical concepts.
Could you speak louder? I can't hear you.
Yeah, my question is if you want to make sure you fine-tune some of your statistical concepts like curve fitting, etc., do you recommend anything?
If you want to fine-tune your conceptual knowledge of this, are you saying is there a book I recommend?
Concepts.
These statistics concepts. Let me see. So there's a very good book. It's called I forget what the exact words for it are. It's called ISLR. So you just do a Google search on ISLR. Yeah, I can actually do it.
Yeah, it's an introduction to statistical learning. Is that the?
Yeah. So okay, so I won't bother then. So that's it's a free book. It's actually quite good. It's in R, which might make it a little bit more complicated. But it does cover a lot of these statistical concepts really, really kind of well. Just to give you an idea, this course will go off in a much more advanced direction. It'll go off into something called complexity theory. It's going to be a free course which is on our platform, but it's not one of these courses which is going to be there tomorrow. I'm developing it as we go, and I'm putting it up as we go. So you'll be emailed whenever there's a new version of it. But it'll also be kind of fun, and it actually goes into at a more deep level as to why these models work. But it's not going to give you any skills on how to fit these models and how to use these models. If you want that, then Pavlos' course, AI1 is the place to go.
Hello, Rahul. I wanted to ask one question.
Yeah.
So as you said, complexity, as you defined it, I wanted to confirm it. Complexity, is it the degree of polynomial, or is it the number of parameters we're using to predict the target variable?
So the number of parameters goes up with the degree of the polynomial, right? So if I have 30 degree, then I have 31 parameters. But more generally, it is what you said it is. It is actually the number of parameters. And in fact, in neural networks, there is no notion, for example, of the degree of a polynomial, but there is a notion of how many parameters you have.
Right.
And one of the fun things about neural networks is you can have millions and millions and millions and even billions of parameters. Like I think GPT-3 has more than 1 billion parameters in it. Somebody should correct me if I'm wrong. But these things have high degree of what's called regularization to fix them. But now you're very well set up to learn about regularization if you wanted to do it in Pavlos' course or on your own or whatever, because you have all the concepts, behind you.
Okay, thanks.
Rahul, we have a question in the chat. What books go really well with Master in AI and DSE course?
So which part of Master AI and DSE? Let me ask you the question back.
Vikesh, can you hear us? If you can explain the question a little more clearly.
Yeah, Rahul. So basically, if I want to prepare, for the accelerated part and then for the advanced part, which books do you think would go really well with it?
So accelerated ISLR would be my recommendation. It's absolutely fabulous, and it's written at a level where you can actually read it. Read it extremely fast.
Okay, thanks.
Yeah. So but for like the more kind of advanced stuff. Let me just think of. So actually, I'm going to recommend. Let me just gather my thoughts for a second. I'm going to recommend 3 or 4 books for this. So there are 2 relatively cheap books available only on the Kindle. They're by this guy Andrew Glasner, and they are an introduction to deep learning. But they're not just about deep learning. They're also about a lot of machine learning concepts, and they're really good. And they're actually readable like you were doing some kind of night reading. It's not like super dense, so you can read it kind of fast. So I think that's my sort of like go-to if I don't want to read things in a very dense way, and he does a very good job. ISLR is more dense, but it has a companion book which is called ESLR as well, which is even more dense. But both of those are actually really good books as well to get prepared. The second part of the accelerated course actually has AI too, which goes a lot into convolutional neural networks. And for this, I can suggest the book I would actually suggest, which is fairly good, is written by the guy who wrote Keras. There's a book by Francois Chollet from Manning Publications, which does actually a really good job of even going into the sort of like science of it, but also how to program it. So I personally found that book actually extremely useful. Yeah. If somebody could just look it up and put it into the chat, that would be super.
Yeah. We have another question. How do you evaluate unsupervised learning models by Teja Ramesh?
How do you evaluate unsupervised learning models? Oh, that's like a question that would take a million years to answer. No. Point is that it's very hard to evaluate unsupervised models. So, for example, if you're looking at natural language processing models, you use a concept called perplexity, which sort of tries to answer how, in some way, how natural what a human would do on it. If you're looking at how many clusters are there in some kind of clustering problem, often you'll have a human looking at it, or you'll try and calculate some kind of distance, intercluster versus intra-cluster distance to do some kind of evaluation. But the truth of the matter is, for unsupervised learning, you just have to do it fresh each time. It's not as simple as supervised learning, where I can use something like a squared error or a cross entropy for classification.
I have a question.
Yeah.
So we had a little bit of or too much of noise, right? So do you think looking into outliers would help?
So whether they would improve the prediction of the model?
Yeah.
Is that the question? Yes, so it always helps because the outliers will send models away somewhere else. But I think if you actually looked at our noise in our, in the curve, if you remember that orange noise in the population I was showing you, right? You probably see that orange noise wasn't terribly outlierish, right?
Yeah.
It was fairly close to the curve, and
no, but
still we got horrible fits if you went to too high a complexity. So if you have things which are really outliers, they will knock your model off its head. So it's good to remove them. 3 sigmas out, 4 sigmas out, okay. Absolutely. But I would be very clear. I would be very, very wary of taking out stuff at the edges, which might be a temptation.
Right. Okay.
Yeah.
Okay. So one more question here. When we have outliers which are really very huge, like the distance is really huge, so is it recommended that do we replace them or do we take them out totally?
Okay. So my own personal recommendation would be to take them out totally. And the only way you would replace them by some kind of like, by some kind of fashion is if there are enough of, enough of other things in that area which are not outlying. So if there's any kind of pattern in the other stuff, then you are pretty sure that that's an outlier, and you can replace it by the average of the other stuff. So there's an entire science to these things, and Pavlos will probably be covering at least some of it in his course. as to how do you replace
Right.
data by other stuff. There is a third option that you can actually, in this, especially if you're doing something called Bayesian statistics, you can model these as outliers in Bayesian statistics as well. So it's kind of the best of both worlds, in which you say, okay, it's an outlier, and I'm going to use a model which says that it's an outlier, a statistical distribution called a student's t-distribution, which says that it's an outlier. But I'm going to at least give it some weight in my fitting.
Right. Okay. Thank you so much.
Yeah. So what I'm going to do before so you have access to the site, but you actually don't have access to the exact code repository. So I'm going to make those code repositories public so that you can access that as well. If you see over here, there's a link over here which says GitHub. And if you go on that link, you can go and actually download the code for this particular thing, which is noiseless learning. Right? So I will go and make that code available to you guys. So you can play with this if you like to do that. But if there are any other questions, they don't have to be about this topic, right? They can be about our classes and all that as well. If you want to know more about our platform, I can answer questions on that. It's a kind of ask me anything type situation. So feel free, just feel free to go ahead and ask me. In the meanwhile, I'm actually making these publicly available. Yeah.
I asked you a question, you remember, about like if we have a situation where there are like bias sampling. Okay, maybe we can consider. Yeah.
Yeah. Okay.
Like,
So let me answer that one, right? So what is the what's the correspondence between bias sampling and this? So let me actually try and answer that by let me find my annotation window over here by drawing a little diagram because that might help. So share screen. I'm going to get the whiteboard up. Okay, so what does bias sampling look like? Bias sampling looks like this. I'm trying to predict this curve, right?
Right.
My bias sampling is when you give me data over here. Usually it's much more multidimensional than that, but just as a simple example, I have data over here and I have nothing out here. Whereas other general ways of sampling may look something like this. You know, if I have 5 data points, I might have them here, 3, 4, 5. And if I have another sample, just because they have only 5, I may get into a situation where I have them here, which is very common, very much what you have. So it is possible, though extremely unlikely, but possible, that random sampling can give you the same answers as bias sampling, which is a very bad model, which does extremely well over here. So this is my f of x, right? Let me actually go for text. This is my f of x, right? And I try and fit a g now in some hypothesis space, which looks something like this. So normally I might get a g with a 6th order polynomial, which looks something like that or something, right? Which is not bad. But if I only have those 6 points, I'll have something that just does an extremely good job going through the 6 points, and then maybe goes off like this, or goes off like that, because I have no data here to fit on, right? So in that case, what's happening is that this random sampling is looking very much like this purposely sampled thing, which was unbalanced sampling over here, and that can happen. So the question is, how likely is it that this random sampling happens? Well, that depends upon your number of points. Right? You can think about it as a kind of like, binomial type sampling, where I say, I have a set of 5 points which are below a certain value and everything else is above that value. What's the likelihood of that happening? So to 0th order, it's roughly, speaking, going to be something of the order of like 100 or like in this case, 100 choose 30. Whatever the probability of having your data over here is, to the 30 and the rest to the 200 minus 30, right? That will give you the rough odds of this happening. But you know that this has happened in the past. Kohli has lost 5 tosses in a row out of the 100 tosses he might have done. So it is possible. that you will get runs where you get 5 tosses in a row which are lost. So it's possible that if you have a very small sample, then it starts looking like an unbalanced sample. Does that answer your question, or did I just totally go off in the wrong direction?
It partially does.
Okay.
Hello.
Yeah, go ahead.
I have enrolled in the AI1 course. So, what resources should I refer to start preparing for that?
So the ones which are in the chat right now.
Just
so
that.
go to the chat.
Yeah. Okay.
The Glassner book and the deep learning book. You can also go to the website. The website has information on this. So just go to welcome.univ.ai.
Okay.
There, click on AI1 or accelerated. I forget what it's called exactly. Why don't I share my screen and we'll do it together? Here, let's do it. So if you click on AI1 over here, it gives you some information about it already. What topics are there? I don't know if it gives you reading. Maybe if Varshini is online, maybe she can tell us more. No, I don't think there is information here. So I think I can get more information from Pavlos on it for you. Totally just log on to Discourse, and we can start chatting there already. In fact, I'll make an AI1 forum today, so we can start chatting there on it. But the resources on this, which are in the chat, stop share? Where did the chat go? Are actually extremely useful. So, and I would say, go read the Andrew Glassner book. It'll get you exactly in the right place, and you'll be able to read. You'll be able to read it at almost the rate of like about maybe 2 chapters a day. It's a simplistic book, but it's really good, beautiful diagrams and stuff like that.
Hey Rahul, so on the welcome.univ.ai page for AI1, there is a list of prereqs that needs to be done.
Yeah, but is there a list of books that people could read? There is a list of prereqs? Let's go look at it.
Yeah. They have given a additional list there. Just scroll further down. Down. Further. Yeah, course prereqs. Go slightly lower. And you'll see please find more detail. Yeah.
Preparing for this course. Okay. Okay, there's a lot of stuff over here. Tutorial on, and different kind of like, there are a whole bunch of like different tutorials for Python, NumPy, and all of these kind of things that they've suggested for you over there. So there you go.
Yeah, I'll go through it.
Yeah. Yeah, but if you want to go into the machine learning parts itself, then I would say go off to Andrew Glassner's book or the ISLR book. Okay. And we should ask Varshini et al. To put up some textbook suggestions on this page itself. So stay tuned to this page. Look at it again in about a day or two.
Okay.
Yeah.
So I'm considered a beginner in artificial intelligence. So should I go for masters in AI or should I go for AI foundations? Because the last time I checked, AI foundations was there in master in AI.
So the foundations course just finished. So, and it was more about things like the mathematics, statistics, and Python programming that you would want to be absolutely comfortable in AI1, AI2, and so on and so forth. You can get that comfort by doing other things like they've suggested on the webpage. You don't have to go through the foundations. So you may want to, think of AI1. The master's program, remember, it goes back with the first 4 courses and then goes into more advanced stuff. So there are the two possible choices. You don't necessarily have to do the master's program. You can do the accelerated too, which is just the first part of it. So depending on what you're feeling comfortable with and what you've kind of decided to do with your life, if you know you're going to go into AI, I would suggest that do the master's program. If you're not sure of that, then I would say do the accelerated, because the accelerated will give you the data science stuff, the AI stuff, and everything. And after that, you could do just about anything you wanted, right? So the master's is more for people who know they want to do AI, whereas the accelerated is for people in any field who want to have the AI skills that they can kind of accelerate their fields. So I very strongly suggest, by the way, to people. A lot of people come and tell me, "Oh, I would like to do this computer science stuff," and they are not computer science people. Think about your own subject, especially with respect to neural networks. The tools that are used in neural networks are now pervasive in almost every field. In my own field, which is physics, everybody uses machine learning in some fashion or the other. In some other fields I worked on, so for example, I worked on in oil mining. The neural networks, for example, very pervasive, and you can make a lot of money by joining oil. I mean, oil companies a lot of money. That's sort of my point. By doing AI stuff for them. Medical imaging, all AI now. Genetics, a lot of AI now. So it's everywhere. So think about not necessarily getting out of your own current subject, but doing this in addition to your own current subject, so that you become the top person in your own current subject. Does that make sense?
So Rahul, let me add a few things.
Yeah.
One is that the accelerated program, essentially, as Rahul mentioned, is the first half of the master program, right? So the good question is, why should anyone take the master program at all? Why don't you take just accelerated and then take the advanced programs later? Well, I think it depends entirely on what your plan is. That if you want the opportunity to be exposed to somewhat longish term projects, the ability to do research with some of us, or just generally do more things than just do the course. The longer that you hang out in the program, the better the opportunities you will get to work with various faculties, TA, RAs, and other things that may come along. 6 months is not nearly enough for anybody to become anything substantial, right? I mean, unless of course you go on studying on your own. So what's the difference between doing just, one half first, another half next? Well, the big difference is we know your commitment is for the long term. And so we are also able to commit resources to the longer term. If we know that you are here just for 6 months and the next 6 months are uncertain, then clearly whatever opportunities are there for other things will be prioritized to those who are there for the long haul. And hence the point of taking the 12-month program right away, as opposed to half first and half later, right?
Mm-hmm.
And so there are lots of people who come in and say, oh, I know the beginning stuff. Should I take just the advanced stuff? I said, your choice, but I think you can join early and not really do all of the coursework if you've taken, and focus on doing other things with us. Be associated with the system much more than, whether it is one lecture you go through or 10 lectures you go through. So that's sort of the larger point in being associated with the master program, which is structured a lot like you would do a master's degree or a degree program at a well-known university like either Harvard or.
Yeah, I mean, we've structured it as a research master's. So, the master's programs at Harvard, you do a bunch of courses, and then you do research with a professor, or you do a capstone course, and we have a capstone course in our program as well, where you're being embedded either in a lab, in a research lab, or in a company. And you're actually working for that company along with us. So we advise you on it, but the people in the company advise you as well. So it's a weird kind of internship, if you like, right? It's not just you're interning inside the company, but you have the advice of your advisors while you're interning inside the company.
Well, not all that weird either, because I think most people who take on this course of studies will discover soon enough that just having learned isn't enough to get you a great sort of career opportunity.
No, I agree with that, Siddharth. The point I'm trying to make is that it's actually an internship plus.
Yeah, right.
Because it's kind of a little bit of an amped up internship, because you are actually having advice from not only within the company but from your peer group as well as from your professors. And that's exactly how Harvard does it. And it's called the capstone program at Harvard. And so it's an extremely popular course.
So our experiences from dealing with a lot of the student questions. So everybody's trying to figure out, oh, what is the three courses that I can get at very low intensity, low engagement, low cost? Well, not the point at all. The reason you show up at an MIT is because you get lots of different things in that 12 to 24 months that you spend there. And therefore, when you go out, you get $500,000 in salary. Now, are we promising you the $500,000 salary? We don't know, right? I mean, but you will certainly know as much as that particular person who goes to Harvard or MIT might know. I mean, in the same range, right? Without making an apples to apples comparison. And therefore, what happens to the employment opportunities that accrue after that? Well, as it turns out that all the people who've created this institution are rather well connected and and we are putting in place a fabulous careers program, right? So to the extent that the point is to demonstrate your learning, in addition to learning, we're going to arrange that. So since any of you who are interested in doing courses are inevitably going to ask these questions, what happens to jobs? What happens to research? Should I do masters? Should I do basic? So I'm kind of laying it out as a structure. Longer engagement with anybody, a mentor, wherever you choose it. Inside our system, inside a university, your own personal, learning environment, great, do it, right? If you'll see some of our other webinars, you'll see this point repeated over and over again, that get a mentor. That's the best thing that you can do for your learning experience. The second thing I'd add to it is work on projects of increasingly greater difficulty, potentially live if you get a chance, so that you can get to flex your muscles and demonstrate them to future employers. Because beyond a point, courses are just courses. Whether it is programming or any other skill that you want to demonstrate, courses means that at some point you have to be trained by somebody, whether it is inside a company or whether it is outside by a course that actually takes care of the training. So make sure that your learning experience encapsulates both, that you get all the coursework necessary and then be trained on actually doing something real, right? Which is why in my first message, I kind of mentioned that we are going to roll out learning that's substantially project-based and kind of makes the process of lecture-based learning a little bit lighter, more optional. So we'll give you information about all that as we come up with it on the Telegram group. So everybody's encouraged to join that. And so I think that more or less addresses most possible questions in the system. So if you have any more left about our learning programs or research programs, please feel free to ask. But I think that's more or less about all we have to say.
Hey Siddharth, we have another question. When is the next cohort of master's program starting after the September 15th one?
Probably 6 months down the line, but not certain that we will have a very similar cohort. We are evolving our programs, so you might have something different. So we'll have a cohort in January, which forces you to choose, unlike the master program where you learn everything in for example, sort of introductory machine learning and introductory data science before you choose whether you want data science or machine learning. In January, we'll have an opportunity for you to just join one stream or the other without the option to actually get introduced to the other field, depending on which one you use. Then 6 months from now, we'll probably have another intake of the master program. But since we are evolving our programs, I'm not sure that they will be the same as what it looks like now. We might drift towards different instructional and programmatic structures. So in some sense, I'm saying that this first flagship that you are doing might, at a very high teacher to student ratio, or rather low teacher to student ratio, few students to a teacher, very, very tight, high intensity, highly mentored experience, possibly might be unique and for this time only. So I'd say anybody who's considering it, jump in. You'll probably not get a similar experience again, at least, anywhere around. It just doesn't exist, this level of professor to student ratio and live interaction. So that's sort of my speech on that.
Another question, when is the next Foundations for AI course, the KTF beginning?
the next one?
Probably September, October. Rahul needs to decide whether we're going to do it live or as a recorded / mentored session, right? By that, what we mean is that all the past lectures will be available, and but all the other things that we've done, we have tons and tons of TA hours where we review the lectures, the material, the problem sets, the homework, and so the next foundation program, I think Rahul might be better placed to answer it, but I'm not sure he knows it either. But the time period is kind of
No, I don't know it either.
Yeah.
Yeah. But the moment we know, we'll let you know as well.
Time period we know, September, October.
It won't be in September.
Yeah, okay.
Yeah.
So, but not the nature of the program.
So I'm currently in the second year of my computer science BSc degree. So I'm very interested in like going to Harvard and all. So how will, suppose if I take the master's program, how will I get help, or how can I get into Harvard? In the website, they told that the master's program, we can get into Harvard or UCLA, like that.
No, Vinayak, I don't think we said you can get into.
No, there are chances like.
Well, so it's very simple, right? If you apply to Harvard or CMU or wherever today, you'll be applying on your own. Your recommenders will be your professors. And if you were familiar, if you had the opportunity to work with Rahul, Pavlos, Achyuta, and of the many other professors who are also coming on board, then you will get, so for example, if Pavlos were to recommend you to Harvard or Rahul were to recommend you to Harvard, you'd imagine that it means something entirely different, right? And of course, if you were to impress the professors even more, they can bat for you to get you admitted. That depends on how much conviction they have in your what do you call it, your scholarship and your accomplishment. So this kind of an opportunity to interact very closely with a professor who at one of these big universities is almost impossible to get, right? So that's how you get in.
Yeah. Let me add one more thing to it. It's actually really hard to get into the master's programs at these universities. So the kind of experience you have over here by with the opportunities to do research and the opportunities to do a capstone type course will actually increase your chances hugely. Just to give you an example, I actually was on the committee that looked at all the applications for Harvard's data science program last year. And it's a pretty competitive program. And I had to look at 200 applications, and I had to choose from those 200 applications, I had to choose about 30 which went on to the next level before culling further. But each one of those 30 applications I chose actually had a non-trivial paper or capstone project which they had done. Nobody who didn't have one of these projects actually even got it. Just to give you an idea of the competitiveness of most good quality data science programs. So that's why I'm saying that even if whether you do it with us or whether you don't do it with us, just do stuff. The doing is actually important.
Okay, fine. So I have another question about the capstone project in the master's program. In the capstones project, we have to go to a company and there we'll work on some project along with guidance from the mentors.
The professor. Yeah, so you'll have essentially, so let me give you an example of a capstone project. So one of the ones that I did with a bunch of my students was we went to TripAdvisor, and TripAdvisor wanted us to look at all the reviews that they were having and actually classify each review on a multi-axis scale. So they wanted to know, okay, so this review, what does it say about the location of the hotel? What does it say about the service? What does it say about the cleanliness? What does it say about all of these things? So we came up actually in about in the course of the capstone a system by which they could do it, which combined both a certain amount of machine learning and a certain amount of Bayesian statistics together to to essentially give you results. If you had a lot of data from the reviews about a place's food, and you were able to extract that using natural language processing from the reviews, then you got some nice information for that particular company, for that particular hotel. But if you didn't have that much information, we had a nice Bayesian way to use information from all the reviews of that hotel and all the reviews of hotels around it to actually get some idea about things. So we had this very interesting way to combine information. And that project took about a semester to complete. And I think then TripAdvisor has adapted some parts of it into their recommendation systems. Another example that I worked on was to sort of predict Ebola outbreaks using social media. So that was a natural language processing plus SEIR modeling project. SEIR modeling is sort of epidemiological modeling of the type you might have seen in these predictions that are being made right now for COVID-19. There's all kinds of interesting stuff that you get to do.
So will the capstones be issued to us, or we can select one of the capstones if there are many?
Yeah, there'll be multiple projects, and depending upon the demand for the projects and all right, we'll allocate them to people, and you have a choice, of course, as to which ones you want to do. But the way it works is that there's usually a finite set of them, and there's usually a team.
So I'll be working alongside other students.
That's right. Kind of like you would at a job, right? You would have a data science team and you'd be doing stuff. That's exactly what it's here.
So I have a question.
I mean, at some level, what we're
So
go ahead.
I am right now working in the field of data analysis, and I wish to jump into machine learning and more towards AI. So what would you recommend? Like, what skill set do I develop, or where do I go to, or what do I read to further get into?
Well, let me ask you a question, and that is as a data analyst, what skills do you have?
Right. So projects I have worked on, one would be on financial analysis. Like we took a good company's, like a company's sales data and basically their account side data. And we prepared more of customer related reports like customer churn, how the customer performs and their trends.
Okay, so let's back up a second. Let's talk about the customer churn example, because that's a great gateway drug example to get into machine learning. So what kind of analysis did you do there?
So we did not a very in-depth analysis, but we mainly compared the customers from the previous year to current year. Like the basic overview is that.
Okay. Yeah. So now, so you've basically done this comparison using visualizations and things like that, right?
Yes.
So you've already started off, with getting the skills that you need for this. That's the first thing you need to do in any data science project. Now, the second thing is, how would you sort of like analyze this using a machine learning model? How would you use past year's customers' behavior, whether they churned or whether they didn't churn, to predict whether this year's customers' behavior? And then what kind of recommendation would you make, to your boss to do? So those are the questions you want to try and answer where you are. And so you don't necessarily need AI for this kind of thing. You can just do it with machine learning, but there's a whole bunch of interesting problems that you will deal with in doing this. So one of the ways, given that you're already working in this, that you might want to do is to just think about this from the perspective of this project, right? Where you're doing this churn prediction. And look up churn prediction on the web. I can do this particular book by Foster and Fawcett. It's called Data Science for Business. And it's by O'Reilly Publisher. It's really good in explaining this and how to deal with churn and that kind of stuff. So my suggestion to you is to think about this from the perspective of your job currently. Do some basic machine learning type stuff. AI1 is a great machine learning course, by the way, and we do talk about imbalanced data sets and things like that in it as well. And once you get a little bit of this machine learning language, either from AI1 or from wherever on earth you want to get it from, think about how you would solve this problem and read up on how you would solve this problem. And I think that's another way of thinking about how you want to educate yourself, because you're going in a very project-oriented perspective.
Right. Okay. So would you suggest, do I stick to a particular tool? Like say for programming, you would use R or Python. Do I go from that perspective or some other perspective?
No, I think the perspective is, are you going to stay in your job?
No, definitely not.
Okay, I mean, so if you were going to stay in your job, I would say, how could you be the most killer machine learning guy in your company? That would be my kind of way of thinking about it. But if you're planning to do something else, then I would just go and learn. Either learn with us at with AI1 or with with however you want to do it. What language, what that you choose doesn't really matter. If you once you get programming, if you know one language, you can learn the other ones pretty easily. Having said that, I think if you're going into AI type stuff, almost everything happens in Python, so it's not a bad language to learn first.
Right. All right. Thank you so much, sir.
Yeah.
So can I also know about how the scholarships work, especially the merit scholarship?
Well, merit scholarships need merit. So apply for a program, fill out the application in detail. Don't short circuit the descriptive questions that are there, and take the test also. And then we'll go from there. One of us will call you, potentially me, will interview you, and we'll decide.
So it's online interviews.
Online is like this, like you and I are talking right now.
Okay,
fine. It's like Zoom, basically, right? These days we're all stuck somewhere or the other because of COVID. So
we must warn you though that anybody who's looking for a completely tuition-free ride, we are not providing those, and but we substantially assist in your tuition payment, but there will always be a cost. Yeah.
Okay, so it was said in the website that there is some module based payment or scholarship.
So what was said in the website is if you top one module, we'll make the next module free for you.
Yes.
Right. So which means that if you happen to top every module starting from the first, you can have completely free education.
So the payment is based on modules.
No, you will have to pay whatever, if you get a scholarship upfront, whatever other than the scholarship, you'll have to pay the entire amount, and you will get refunds for the modules that you top.
Okay. And the scholarship is based on my GPA from college and the entrance assessment.
Variety of things. We don't make the assessment model public, but we are looking at, for example, how well you are likely to do in our programs, and also generally what your life and career goals are, and how will you fit into our scheme of things. So those are the things that we look for. And
okay,
also financial need is an element, right? So I think, yeah. So if you...
We have another question here. As a mechanical engineer, where would AI and machine learning be used in the future? Rahul, I think that's for you.
What's the question?
Mechanical engineers use AI, like everywhere?
Chemical engineers?
Mechanical
engineers, everywhere. I mean, if you're making wheelchairs, robots, any of those kind of things, and you're not using AI, you should be at this particular moment. Yeah, I mean, the use of AI has become so pervasive that each time I see something, I'm like, wow, you could solve that using AI. The other day I read something about how people are doing quantum physics there's a particular kind of model called a FOC model, FOCK. It's actually fairly complicated chemistry problem to solve, and it's been solved by using AI to actually calculate the wave function.
So if I may add, when I was at IISc, they had this department called Center for Product Design and Management, if I'm not wrong. And then there it was mechanical engineers who were working particularly with AI to try and come up with a new automated design of all their curves in those bolts and screws. I don't know exactly. I don't know the technical terms correctly. So they had like a lot of automated ones. They even, so civil engineers, they had CAD for getting, architectural designs. These are two projects I know from that.
And there is something at IISc called the Center for Cyber Physical Systems, which is run by Professor Bharadwaj Amritur. And as the name suggests, it is, computer systems to run physical systems, which might be robots, wheelchairs. Rahul was talking about simple problem, robotic arm, right? In industries, what is the most efficient way a robotic arm can get its job done? How does the robotic arm ensure safety of the people, because these can be huge, of people working around them? What is the least amount of energy that a robotic arm can consume in performing a particular robotic arm task? And clearly these are problems where techniques like reinforcement learning are being applied right now. And then a whole host of things. I mean, there's a list, like looking at defects in an assembly line. Can you do that using imaging, right? And what kind of interventions can you make? Can you stop a production line when you see a defect rate rising above a certain amount, just based on observation and no quantification of that? So the list goes on and on and on. It doesn't matter which field you are in. Machine learning is a tool that is widely applicable across just about anything. All right, folks, it's been almost 2.5 hours since we began. So if nobody else has any other questions, we will call this session to a close. I do want to know, just as a show of hands, +1. I know there are a bunch of people here from our last session with Rahul, but I do want to know who's still actively considering taking the master program or accelerated program that's starting up. There's a reason for that. We are planning resource allocation and we need to close the admissions. So if any one of you is actually still thinking, considering, about to write the exam, or in the process, +1 us here so that we can get back to you and figure it out and close the process.
I mean,
So I just want to know, where can I get the prerequisite list for the master's program?
There isn't a whole list per se, because the whole idea of the master's program is that we teach you from the beginning.
No, it was written that some Python, Matplotlib, Pandas, NumPy, there were some prerequisites before.
Those are the only prerequisites. Whichever you listed, that's the list.
And which, by the way, you can learn alongside also. You don't have to come fully prepared.
Yeah.
You have basic familiarity with Python and NumPy, you should be good to go, as long as you're willing to sweat it out for that. And Subhash, master program here is not equivalent to a master degree, because we are not a degree granting institute. In terms of content, it's pretty darn close. So these are certificate programs, not degree programs. So it looks like no one here is, I'm not seeing any +1s here. So if there's anyone at all, then let us know.
We have one from Sukriti.
Yeah, Sukriti, I already know, been in touch with her. So 9:39, closing in a minute. Please, anyone else who's got to +1, please +1 so that we can contact you. Alternately, do join the Telegram group indicated there. Okay, Sherpa, you're already in, so I'm just looking for people who want to be in. All right, guys. I guess this is it. Thank you very much. Lovely evening. Thank you.
I think for those who are here, the GitHub repos are now all freely available. I've had the code for today's demo. Sorry, Siddharth. Go ahead.
No, I was just saying thank you for coming and time to wrap up. Have a lovely evening, or rather what remains of it, everyone. And have a lovely remainder of the Sunday.
Bye, guys.
Bye. Thank you.
Thank you.
Hey, Rahul, you want to hang in there for a bit?
Sure. You want me to hang in? Sure.
What I wanted to chat with you about.
Or we can just do it offline. Just send you a quick Jitsi.
Jitsi. All right.
Yeah. Okay.